Yeah. So now we start to talk about supervised learning. So supervised learning is actually one of the most emphasized area in the last couple of decades. So we do have a lot of research going on for this supervised learning. So one easy reason is that we know how to evaluate our performance, whatever model that we propose, so we can easily evaluate how good the model is based on, for instance, the accuracy. You use accuracy error rate, or you sometimes you use F measure, right? So this kind of information will be, let's say, very clear, so that we know that the model could be, let's say, good or bad, right? So given that, so a lot of research going on in the last couple of decades, just like I say, so we know we can propose, we can try to find out better and better model. So that's why supervised learning is very active. It's still very active, okay? But now let's say we focus a little bit more on, for instance, on supervised learning. And if you know that, say, later we're going to talk about deep learning, for instance, right? So one of the reasons why the deep learning is very, let's say, successful, just because one reason is that in deep learning, somehow it combines supervised learning and unsupervised learning together, so that later, let's say, and they can use the information from both sides, so that we can get a better result. Okay, so we're going to today for the first topic, first part, that we're going to give you one easy example and to illustrate what the supervised learning is all about. So later we talk about regression problem, and also probably today we are not going to talk about PAC learning and the VC dimension. Okay, so we are starting from a easy example to illustrate what the supervised learning is all about. So suppose that we got we win lottery, right? So we win lottery. Some people like you are very young, right? So maybe you want to buy a sports car, right? So then we are going to, let's say, find out, for instance, because we were not rich before, right? So we didn't know what the super sports car is all about, right? So we want to, let's say, go to the web to find, okay, what could be a sports car, right? What could be a sports car? So the web will tell us a lot of things, right? So instead of typing maybe like a sports car, right? So we want to let's say we want to find some other information to help us to classify between, let's say, sports car and non-sports car, right? Sometimes it's not cannot be so easy, right? Because some car may not be called sports car, even they are sports car, right? Okay, so we want to based on the web surfing, right? Maybe we find out a lot of objects, right? So some of them could be, let's say, sports car, right? That we like them to be positive examples, right? Some other could be non-sports car. We could make them to be a negative example, right? Then the next is to find out, can we separate between, let's say, sports car and non-sports car, or positive and negative, right? So in this case, it's very easy because we only have binary choices, right? So either positive or negative, right? So from here, that you can quickly come up with, let's say, for this kind of binary classification, uh, the easy thing is that even that you know nothing, even that you don't get a lot of information, you can still try random guess, right? Random guess will give us 50%, close to 50% accuracy or error rate, right? So that's something you need to keep in mind. So for instance, for binary classification later, if you want to focus on real problems, then maybe for binary classification, usually the accuracy above 80 or even 90 should be something reasonable. On the other hand, if the accuracy is like 70 something, right? Usually it's not that good. Usually we don't show this kind of exam result to others, right? If the result is like 60 something, right? We don't even mention it, right? Because it must be some kind of error, some kind of bug, a programming bug, right? So that's something that you have to keep in mind. Okay, so we want to learn a sports car, right? So it's a concept. Actually, we call it's a concept. So maybe I should write it down. Yeah. The camera is laggy. You don't care about that, right? Maybe yeah. Sometimes it'll be a little bit delay. But as long as the audio is okay, then I think it should be fine. It should be fine. Okay. Yeah. So we are talking about concept, right? So we are talking about concept. Whoa, it's like upside down. Yeah, I try one more time, right? Okay, the concept in machine learning is something that we want to learn. Okay, something that we want to learn for classification problem. Okay, for classification problem. Yeah, so usually if you write paper, right, you don't use concept. Okay, I mean if you write machine learning paper, right, so you don't try not maybe you should try not to use the concept, right, because concept is some certain keyword reserved for machine learning target that we want to learn. Okay, yeah, so we want to find we want to learn a concept, right? So in this case, the concept is like a sports car, or uh, which one is sports car? I mean, given some kind of information, then can we predict it's a sports car, yes or no, right? Okay, yeah. So then later, what? By the way, then you can find, the content. Many of them will be from this book, right? Now it's like third edition, so I think you can take a look more details if you want. Yeah, so then we want to learn what is concept, right? So we are given what kind of input that we have, okay? So apparently that you can collect a lot of information, right? Something that would be related would be helpful for us to understand what is sports car, right? Suppose that here we just randomly choose two items, such as one will be price, right? The sports car usually will be not so cheap, right? Okay, and engine power, right? Engine power, like sometimes it will make a lot of noise, like this kind of, in the nighttime, right? You usually see some, crazy boys, right? Drive, the sports car everywhere, right? So the engine volume will be something usually to separate between sports car and non-sports car, right? So now uh, we have two attributes, right? Apparently, we can go on to collect more and more attributes, right? But here, that's because we want to illustrate the idea to you, right? So that we want to show it in two-dimensional space, so that we don't try to find more attributes. Okay, so by the way, so here we also want to say that given, let's say, a concept that we want to learn, right? More attributes usually will be helpful, right? But we need to make sure that the model will be capable enough to fully use those attributes, right? If that's not the case, more attribute means more disaster, because more attribute means that the model is harder to train, and also the prediction, when we need to use the model to predict the future, right? So usually it takes longer time, right? So we don't want to include more features if it's not necessary. Okay, and given, let's say in this case, there will be the attribute set, right? So then we will have a label y to denote as either as a positive example, meaning a sports car, or non-positive example, meaning it's a non-sports car, right? Okay, then in the end, everything will be, it will be everything will be represented by this kind of x and y, right? X will be the attribute, y will be the label, right? And in the end, we're going to collect a lot of data like this, right? Could be m number of different data. Okay, so the data could be like what? For instance, the data could be like this, right? So we will have some positive data, some negative data, and looks like the positive data is close to the center, right? So the x-axis will be the price, y-axis, x2 will be engine power, right? Okay, so as you can see that based on the data that we collected, right? So there'll be many of them around the center, right? They are considered to be sports car. Okay, so yeah, anyway, so that's what we have collected as our input, right? So based on this input, we want to do something. Right? Can we separate, for instance, between sports car and non-sports car, or between positive and negative examples, right? So maybe we come up with some kind of so-called rectangle classify. Rectangle classify means that, okay, maybe we want to say the price between P1 and P2 and the engine power between E1 and E2, right? Then they'll be considered sports car. Otherwise, they'll be considered non-sports car, right? So then we come up with this pink rectangle. So the inside, this rectangle will be positive, right? The sports car will classify as a sports car. The outside will be non-sports car, right? So that's what we guess. Okay, we don't know if it's true or not, right? So by the way, we want to say that oh, sorry, I should give you this, right? Okay. Yeah. By the way, usually when we say hypothesis or model, right? Okay, that means the same in our presentation. Yeah, in our presentation, hypothesis and the model will be the same thing. Okay. Yeah, sorry about that. I didn't show you the whole thing, right? So yeah, still any laggy? Yeah, looks like a lot of people doing anyway. Yeah, so any questions here? So when I say maybe after a few seconds that you're going to hear it, right? So it's okay, right? So you can just, whenever that you will have problems, you type and I'm going to see it. Okay. Yep. So let's come back. Yep. So we will have here we will have so-called the rectangle hypothesis, right? Rectangle hypothesis or rectangle model, okay? Just like I say, hypothesis is just like a model, okay? The same meaning. Yeah, so we will have hypothesis, we will have the rectangle hypothesis or rectangle model, but we don't know it's correct, okay? Could be yes, could be no, right? So maybe the here, okay, we found out the following, right? So let's say this part is actually the real concept, the real concept. This will be the real concept, okay? Instead of, you know, the pink one. Pink one, I think we can just go back to this one, right? So that's the what we guess, okay? That's what we predict. That's what we come up with as a so-called hypothesis or model, right? So here, the blue one, you know, the blue one is actually the true concept, the truth, okay? So as you can see, there will be some kind of disagreement, right? Disagreement, okay? So disagreement actually are actually those four green area, okay? There will be green regions, right? There will be that we have a disagreement. But if you check it carefully, right, all the green area contain no data points, right? The data points will be maybe here, right? Maybe here, right? Maybe here, okay? Maybe here, right? Okay, but none of them are shown in the green area. None of them shown in the green area, okay? So which means what? Means that, okay, even let's say the true model and our hypothesis may not agree with each other 100%, right? But we still say the hypothesis is consistent with the data. Consistent with the data, okay? Consistent with the data meaning what? Meaning that we can classify using the model, we can classify all the data points with 100% accuracy, okay? That's what the consistency is all about, okay? Meaning that no training error, okay? Yeah, so so let me just, oh, I'm too big, right? So maybe just put aside. Yep. Let me just make yeah. So what we want to talk about is like the following, right? So we have usually given the data points, right? A bunch of data points. Usually, especially when the data point is not too many, right? So maybe we want to find a concept. Sorry, we want to find hypothesis so that we can enjoy, you know, no training error. Okay, which means that we say the model or the hypothesis is consistent with the data, right? Consistent with the data, okay? But now that we know, given let's say the deep learning and also the big data, right? So usually we don't really care about the consistency, right? We don't really care about the hypothesis is consistent with the whole data points, right? Maybe just 1% or maybe 5% of the data they got wrong, right? With the prediction wrong, but usually we don't care that much. Okay, so whatever hypothesis we have, right? So then in this case, we have a rectangle hypothesis, right? Usually for this rectangle hypothesis, maybe we just use 4 parameters to define this hypothesis, right? So which means that whatever rectangle model that we have, right? We can just simply use P1, P2, and E1, E2 to know what kind of model, what kind of hypothesis that we have, right? Okay, so now that we have a hypothesis like this, right? Okay, and we want to say, okay, how to evaluate this hypothesis, good or bad, right? Good or bad. So maybe we can just say, yeah. So maybe we can just say, okay, why not try to compute the empirical error? Okay, so empirical error will be computed by the following, right? So each time that we have the disagreement, right, h of x means the result computed by our hypothesis function, right? If it's a disagree with yi, then we say, oh, we count one, okay? Then we sum all the things, all the disagreement, divide by the number of m, right? Then there'll be the so-called the empirical error. There'll be empirical error. So basically, we want to find what? We want to find the best hypothesis, meaning we want to minimize the empirical error as much as possible. Okay, as much as possible. Okay, so that's how we choose a hypothesis, right? But actually, what I didn't emphasize is that before we want to choose the best hypothesis, right? Before we want to choose the best hypothesis, actually, we want to first of all find out what is so-called the hypothesis space. Hypothesis space, okay? That's the big H right here. Big H right here. So what is a hypothesis space? Okay, so maybe in this case we can say the hypothesis space is what? Is this hypothesis space is defined by all the possible okay. Yeah, so hypothesis will be all the possible, P1, P2, and E1, E2, right? So they are all, maybe we just say like the following. I mean, if you don't mind, and I'm going to close. Could be the delay comes from the WebEx. I don't know. If you don't mind, maybe we can just simply close. Anyway, so we try later. Okay. Anyway, so that's the hypothesis space is like the following, right? So we will have maybe we choose whatever we want, P1, P2, and E1, E2. That will be the all kinds of possibility, right? That will be the hypothesis space. Okay, so given that edge, that hypothesis space, then we want to find out one small edge that will be the hypothesis, right? So what could be the best hypothesis in that hypothesis space? Usually we use accuracy or maybe empirical error to separate between the good one and bad one. Okay, so that's what we want to emphasize. So let's come back. Okay, so then we want to say what is the complete story of learning, right? So first of all, there'll be a few steps. Okay, the first step is actually choosing the hypothesis space. Okay, like in this case, maybe we are going to choose the hypothesis space to be all kinds of rectangle, right? Meaning that there'll be 4 numbers that we have to decide, right? So all kinds of rectangles. Okay, so that would be the hypothesis space, right? Then given the hypothesis space fixed, right? Then the next is to find out what could be the best hypothesis. Okay, what could be the best hypothesis? Okay, so choosing the hypothesis space is very crucial because if we choose correctly, right, we can make sure, right, make sure what? Make sure the true concept belongs to this hypothesis space, right? So the next issue is to find find it, right? Next issue is to find it, right? So we will have some kind of dilemma. What kind of dilemma we have? The dilemma will be like the following, right? So maybe we can choose, we can use different, yeah. So the thing is, we can suppose here will be the hypothesis space, okay? Suppose this one is the hypothesis space, okay? Sorry, I think I'm going to close the WebEx. To see if the, yeah, hopefully that'll be better. Okay, looks like it's better now. Yeah, so here will be the hypothesis space. Okay, suppose the true concept is right here. Okay, suppose the true concept is right here. Yeah, so whoa, it's really delayed. Okay, so that's the true concept, right? So usually the next is that when we are going to have a algorithm, usually that's the what the learning algorithm is all about, right? The learning algorithm will be, let's say, start from some initial position, right? Maybe gradually go to, you know, this true concept, right? Okay, yeah, but actually that's the ideal case. That's the ideal case. Why we say it's the ideal case? We don't know actually the true concept is really, let's say, belongs to this hypothesis space, right? It could be a lot of different situations, like what? You know, maybe we choose hypothesis, you know, space to be very small, right? Then the true concept is outside. Okay, the true concept is outside. That means what? That means we will never find this true concept. Maybe we can find something close, but it still could be far away from the true concept, right? Uh, or maybe we found okay, we want to, let's say, make the hypothesis space to be bigger, right? So now that's a new hypothesis space, right? Okay, so now we are feel very happy, right? Because the true concept belongs to this hypothesis space, right? Okay, but the thing is, oh, now we know, let's say, if we using this true hypothesis, new hypothesis space, right? We use some learning algorithm. We try to find out the what could be the best hypothesis, right? Maybe we will never, you know, find this true concept, right? We never found this true concept. Okay, so that's the something that we call a dilemma or trade-off, right? Okay, the trade-off comes from, let's say, if we choose very small hypothesis space, right? Maybe the concept, the true concept, doesn't belong to that hypothesis space, right? It's outside of the hypothesis space, right? On the other hand, if we choose the hypothesis space to be very big, right, then the learning algorithm will be harder to write. Because we want to find out what could be the best hypothesis, right? We need to try. Probably you already heard about, right? Let's say, what could be this, you know, learning algorithm, right? So for instance, gradient descent, right? Okay, the gradient descent. So that will be the gradient descent. Is usually, it's not that efficient. Okay, it's okay, right? Sometimes it could be slow, right? Sometimes it could be takes a while. So that means what? That means that if we have a very big hypothesis space, right? to find out the best hypothesis, or maybe find out the true concept, it will take a long time, right? It will take a long time. Okay, so that's something we have to keep in mind, the trade-off. Okay, so that's why we emphasize the issue. The issue is that how to choose the hypothesis space appropriately. Okay, then the next one is, okay, suppose we find the hypothesis space appropriately, right? And we also assume the true concepts belongs to the hypothesis space, right? Then the next is how to find out the best hypothesis inside the hypothesis space. Okay, so that's the second issue. Okay, so given all the things, right, solved, right? So then we say the complete story of learning is what? Complete story of learning is that, okay, first of all, we have a program. So on the left hand side, so we have a program. Okay, so suppose this program is some kind of, we call the skeleton. We call it skeleton. Skeleton means that, okay, we have this learning model, the hypothesis model, actually hypothesis program. So, but we found out that, okay, we call it skeleton because a lot of place will be empty in this program. Okay, those will be actually the place that we call parameters or undecided parameters. Okay, in this skeleton program. Then we will have another program called the parameter estimation, right? Will help us to find out those, to fix those undecided parameters. Okay, once that we find out those parameters, okay, then this program 1 will be complete. Then this program 1 will be complete and can be ready to be used to predict the future, right? So if you are clear enough, right? So what is the input for this program? The program 2. The program 2's input will be what? Data. Okay, so maybe we can write it down, right? Okay. Yeah, so we will have the program 1, okay, and program 2, right? Yeah, program 1 we say is a skeleton, right? Okay, program 2 is the parameter estimation. So program 1, what is input? So what is the output? And also for the program 2, so what's the input? So what's the output? Okay, so if we start from program 2, right? Because it's actually the first one to do, right? So the input is the data, the big data. Okay, so the output is parameters. Output is parameters. Okay, so that's the input and output for program 2, right? For the program 1, that's what we call the skeleton, right? So the input will be x, okay, new x. Maybe we say new x plus parameters, because parameter will be obtained from the program 2, right? So once we finish program 2, given the data, then we have the parameters. Then after we have parameters, the program will be more or less fixed, right? Then we have a new x, then we can output new y, right? Okay, so as you can see that the program 1 is used for prediction. Okay, program 1 is used for prediction. Program 2 it used for training, right? Okay. Yeah, so that's for prediction. Okay, so here is for training. So yeah, so any questions so far? I think the speed is better now, right? Yeah. So that's what we have. Okay, that's what we have. The complete prediction, right? I mean, complete story of learning, right? So we do have two programs, right? So one is for parameter estimation, right? Because for another program, we do have a lot of empty space for us to fit in, right? Okay, so then you understand what's going on. So between, let's say, the current, let's say, the machine learning approach and the traditional approach, the difference is what? The difference is that before now we only have, program one, okay, and it is not really a skeleton, right? Because the all the empty space will be fitting already, will be fixed already, because some domain experts tell us what those empty space should be all about, right? So maybe the domain expert will help us to fix those undecided parameters, right? Like, for instance, if we want to, for instance, yeah. So for instance, if we want to, let's say, if we want to detect a human face, right? So if we want to detect a human face, right? Okay. So if we want to detect a human face, right? So we are going to see, oh, what the eye is, right? Okay, the nose and the mouth. Sorry, yeah. So then we're going to say the following, right? So and maybe the parameter will be, okay, the eye will be, let's say, with the width and the height, right? Okay, okay, because we got two eyes, right? The width and height, right? Okay, and also the nose, right? There'll be some other parameters, right? Maybe another width and height, right? And the mouse, right? And also, right? Okay, so those that we call the parameters, right? Once that we decide the parameter, we can use it to detect different people, right? And human faces, or maybe we can recognize different people, right? Okay, so but before now, the traditional approach is more or less like, for all the parameters, right? All the parameters, for all the parameters, right? For all the parameters, they are basically, fixed and decided by domain experts, right? Okay, so that's not so good, right? Now that the modern approach is that, why not use the data to learn by itself, right? So the model can be learned based on a lot of data. So once the model has been learned, then we have those undecided parameters fixed, right? Then we are ready to build this skeleton program, okay? So meaning what? Meaning that the skeleton program provides more flexibility for us, so that the result could be more robust than before. Okay, yeah. So uh, as I mentioned to you, right, there'll be issues, right, like deciding hypothesis space. Okay, and what I can tell you is the following, right? So for between those different issues, right? Okay, the first issue, decided the hypothesis space, is actually harder, right? Once the hypothesis space is decided, the rest is relatively easy. So that's what we can say, right? So the second part, right? Once the hypothesis is decided, the rest will be easy because later we're going to come up with all kinds of learning algorithms, right? Based on those learning algorithms, so we are all finding the best model with low error rate or low, let's say, or good F major, etc. Right? Okay. So those will be relatively easy. And probably you also heard about a parametric approach, meaning that we have some parameters ready to be fixed, right? Or non-parametric approach means that we don't really have a clear parameters. Actually, we use some kind of it's hard to explain now, right? Basically, we use a set of functions to approximate the could be the true model, could be the true concept. Okay, yeah. So just like I say, right, deciding the hypothesis is very hard, right? So once the hypothesis is decided, whatever who told you that it could be the good hypothesis, right? So once you make that choice, right, the rest will be more or less straightforward, right? Just like if we talk about the rectangle case, right? Rectangle concept, right? So the thing is, okay, once you decide, okay, the rectangle could be the hypothesis space, all kinds of rectangles will be the hypothesis space, right? Then the rest to decide this kind of rectangle may not be so difficult, right? Maybe we just choose whatever between the positive and negative, then maybe we can come up with some kind of model, right? Okay, so that's something we have to keep in mind. Actually the hypothesis, deciding the hypothesis is actually very hard in general, right? And on the other hand, I mean, it's not hard means that we don't really most of the time we can only deal with this issue, like a case by case basis, right? On the other hand, once the hypothesis is decided, right, the rest will be straightforward. So the second part actually, that's somehow that we can teach you, right? Like once that we decide the hypothesis is decided, right, then the rest will be straightforward. Then we can rely on a bunch of different learning algorithms to help us. Okay, so more or less we say that for the machine learning course, right, especially the first machine learning course for you could be, right, then most of the time we focus on this part. Focus on this part. Okay, so I think we can take a break and come back. We can take a break, come back for, let's say,